Okay, so now I want to come to one of the most important ideas in this subject, which is, of course, projectivities. So just before we get to that, let me define the range of a line to be the set of points on it. Or we could equivalently say touching it. And in a similar kind of dualistic way, we're going to define the pencil of a point as the set of all lines touching it. So now, let's say we have some range, so we have a line, and we have a range of points on this line. Maybe this is the set of all points, maybe it's a continuum, maybe we have a finite setup, whatever. But this is the set of all points on this line. And we also have a point. And so the simplest kind of projectivity is what's known as an elementary correspondence. So let's just draw in this pencil here. And an elementary correspondence between a line and a point is when we put the members of the range of the line in one-to-one correspondence with the members of the pencil of a point in such a way that elements in correspondence with one another are touching. Okay? So let's write that down here. So corresponding elements are touching or incident upon one another, as some projective geometers may prefer to say. So in this case here, we have a line, its range has 4 points, and we have a point, and its pencil has 4 lines. And this point is put in correspondence with this line, and that's good because it touches it, it's incident upon it. This point is put in correspondence with this line, which is good because it touches it, and so on here and so on here. So that's a good elementary correspondence. Now, how might we write such an elementary correspondence? Well, let's say that we label these points A, B, C, D, and we'll label these lines of the pencil, little a, little b, little c, and little d. Well, we could write it like this, that A, B, C, D is projective to little a, little b, little c, little d. More generally, sometimes we use a different kind of notation. Or should I say, sometimes Coexeter uses a given kind of notation. I'm not sure if I'm going to use it too much, but anyway, sometimes he would write something like this. He'd write X is in projective correspondence with little x. So what he'd mean by this then would be that we think of x as a variable point on the line, and we think of little x as the image of big X, as in this is the member of the pencil which big X gets corresponded to. Okay, so we could interpret such a statement as saying that this is a projectivity. Remember, elementary correspondence is one of the most fundamental kinds of projectivities. And we could interpret this as saying that it's a projectivity from X, from big X onto little x. And then perhaps we could denote an inverse projectivity, something like this. Okay, well, let's say we have a line here, L0, and it has 3 points on it, A, B, and C. Well, we could be able to do an elementary transform from these members of the range of this line onto these members of the pencil of this big point here. Which I shall call B0. And it might just so happen that we have another line here, called, let's say, L1. And hopefully you can see that this naturally leads to another elementary correspondence, where C kind of winds up here. Maybe I'll call it C dash. B winds up here, B dash, and A dash here. Okay? So we could naturally write this kind of idea as something along the lines of that ABC is projected to little a, little b, little c, which is projected to A dash, B dash, C dash. So what we have here, essentially, you could call it a product of elementary transforms. In other words, it's the kind of thing you get by repeatedly performing these kind of elementary transforms. So this allows us to define the main thing which we're interested in, which is a projectivity. So a projectivity is a transformation from a pencil or range to a pencil or range which corresponds to a sequence of elementary transformations. Okay, so for example, we might start with a line here, L0. We'll have a variable point x on there. And then, well, we might have this point P0 here. And in our first elementary transform, this point on the range of L0 gets mapped to this pencil through P0. We might have another line L1 here. And so this is now x1. And there's no reason why we couldn't have another point here, P1. And again, we can lift this point off the range onto a pencil. So now capital X1 is corresponding with little x1, and so on and so forth. So we can keep going. Every elementary correspondence has to be between objects of different types, points and lines. If we do an even number of them, we'll end up mapping the same type to the same type, as in our projectivity will be, say, from a line to a line, or from a pencil to a pencil. But also we can have projectivities where we just do an odd number of elementary transformations or elementary correspondences. And in that case, we'd end up mapping perhaps points onto lines or whatever. This is really the fundamental idea behind projective geometry, because what we're really interested in are the features of geometry which are invariant under these kinds of operations. Okay then, so I'm defining this fundamental notion of a projectivity as a sequence of elementary correspondences. But there's something important I forgot to say about elementary correspondences, and that is, say you have a line and a point, and you're wanting to do an elementary correspondence between the two. It's important that these two objects are not touching. In other words, it's important that the point is not a member of the range of the line, or equivalently, that the line is a member of the pencil of the point. They ought to be separate. And an exercise for you is why. I'll help you understand a bit about this subject. What goes wrong if you try and do an elementary correspondence within which the line and the point are touching each other? Okay. Okay then, so now let's talk about perspectivities. These are special kinds of projectivities. So let L1 and L2 be lines and let P be a point, and, well, okay, we'll make it self-explanatory. So a perspectivity written like this from the range of L1 to the range of L2 is a bijection might as well give it a name, so F from the range of L1 onto the range of L2, such that for every point in the range of L1, we have that the line that goes from Q to the image of Q under this transform is a unique member of the pencil of the point P. Easier illustrated just by this diagram. So we have, here's our line L1. On its range, it has some points. Here's our line L2. And then we have this mapping. So let's say we have A, B, and C. So our perspectivity can kind of be thought of as a mapping. That's where A gets mapped to, and B, and C, and this is our point P. And notice that if we look at any particular point and we look at its image, that's going to form a line, and the set of all such lines is in one-to-one correspondence with the set of lines of a pencil. So this is this is one of the two kinds of perspectivities. Just to, in case you're not sure about what this notation means, this basically means that we have a mapping which associates each member of the set of points on line 1 with a point on line 2 called f of blah, f of q, and a bijection. That means it's a one-to-one onto mapping. So it never sends two elements over here to the same place over here, and it covers every element over here. Every element over here has something sent to it by f. Okay, so that's the point-wise definition of a perspectivity. We also have, oh, and by the way, this notation under this notation, x would be a variable point on this original line here, and x dash would be where it gets mapped to. Okay, so what about the point-wise definition? Sorry, what about the line-wise definition of this? Well, it's pretty much equivalent, so let P1 and P2 be points, and let L be a line, and our perspectivity from little x, this is using Poncelet's notational device, to little x dash via the axis of perspectivity L is a bijection might as well give it a name, call it F again, call it capital F this time just for fun. It's a bijection F from the pencil of P1 to the pencil of P2, such that for every line in the pencil of P1, we have that if we look at where that line starts and we look at where that meets with the image of that line, we have that that's going to belong to the range of this line L. So we really have something like this. We have, this would be point P1 of a line L, and a point P2. Now, these are points, they have pencils, that means they have lots of lines going through them. And the thing that makes this a perspectivity is that these lines correspond with each other according to where they strike this particular line. Much like in perspective drawing, parallel lines are supposed to meet upon the horizon. So in some sense, you could think of this so-called axis of perspectivity L as acting something like a horizon, where equivalent or parallel lines meet. Okay then, so it's time for me to give you a little challenge to do now. So let's suppose we have a line with 3 points on it, A, B, and C, and we have another line down here, again with points A double dash, B double dash, and C double dash. Now the problem is to find two perspectivities which, when combined, correspond to a projection from this line to this line that maps A to A double dash, B to B double dash, etc. So if you'd like to pause this video now and think about how you might want to draw in extra points and lines to construct such a perspectivity, construct such perspectivities, please do so. Okay, so there's actually lots of solutions. Here's one. If we join A and B double dash, excuse me, and B and A double dash, let's call the point that makes B dash. Similarly for A and C. Now this defines our sort of intermediate axis or intermediate line, because we're actually going to do two perspectivities. So we've defined where B dash is and C dash. What about A dash? Well, to find A dash, we just draw a line between A and A double dash, and we'll let A dash be the place where that meets the intermediate line. So okay then, how does this work? Well now, since we've defined, might as well write down explicitly what we've done. So we've defined B dash is equal to AB double dash dot B A double dash. We've defined C dash similarly. And we've defined A dash like this. Now it can be shown, well, it's fairly easy to see, that if we take A, B, C and we do a perspectivity with or about point A double dash, so we're projecting these guys down here using this as our kind of viewing point or perspective point. So we're interested in how rays shone from this point cause these lines to get projected onto this line. Well, that's going to cause us to get to A dash, B dash, C dash, and then in a similar kind of way, another projection via A actually gets us to A double dash, B double dash, C double dash. Let's just check for the case of B. So, under the first perspectivity, B has this projection towards A double dash, and it goes from here to here. And then secondly, it has this perspectivity with a centre A, which gets it to here. And the same is true for the other points. Now I'll leave it as an exercise for you to show a similar projection can be formed from concurrent lines A, B, C to concurrent lines A double dash, B double dash, C double dash. So algebraically it's pretty much the same setup, but the diagram also should be drawn. Okay, so the final remark of the day, an important thing about projectivities. Suppose I should call it remark 1.1, is that any four collinear points can be interchanged by a projectivity. So for an example of this, suppose we have 4 points A, B, C and D. Now we can add some extra points so that we can swap these things around. Let me just draw some more lines. So it'll become clearer in a minute what I'm actually doing, hopefully. So I've added some extra points, Q, R, T, W, Z, and now, in particular, you should notice that we can do some perspectivities, and we can change around the order of these points. So we can essentially do a projection from this line to itself, which shuffles around the order of these points. In particular, we have that if we take A, B, C, D, and we do a perspectivity about the point Q, well, we're looking at this line and we're doing a perspectivity around this center. So we'll go on to this line here, and that's going to end up sending A to Z, B to R, C stays invariant, it doesn't move, and D gets sent to W. So now we do another perspectivity, this time about A, and we get Q, T, D, W. And if we do another perspectivity, this time about R, we get B, A, D, C. So if you follow this through, what we've actually done is essentially swapped around the order of our points just by making these different perspectivities. And of course, when we compound together these perspectivities, that ends up making a projection.